Welcome, everyone. We have a small crowd tonight. I'm hoping we'll get a few more come in here. You just never know. We've got all kinds of things happening. At the beginning, I just did want to say immediately following their presentation, if you would just go out to the lobby, we've got some items on display that they had brought. That we want you all to be able to get a chance to see, and then you can interact with the team at that time. We have another event coming in this room immediately after. Again, welcome. My name is Crystal Hopper Myers. I run our STEAM Pathways program here at SWOCC, and tonight is pretty special. I am sorry that the crowd is kind of small right now, but maybe we might get a few. I know we'll get a few more in here in a little bit, but this is also being live streamed online. I've already got text messages from people saying that they're on watching. They'll have questions. I'll probably get to you guys in a bit. So today we've got our Oregon State University. We've got AIAA, and these are awesome rocket team leads and participants here to, they're going to actually introduce everyone because I had a list that might change a little and I don't want to get anybody's name wrong that is here or is not. I also always like to say, and actually it kind of ties into this because we have one of our former students, Damian Lilienthal, that actually graduated from SWOCC, engineering student, is now at Oregon State University and doing these awesome things. And we're excited to have him come back with his team. He is part of SPEAR, which is our student research team. And if you're listening online or here and interested in getting involved in student research, please reach out to one of us here. Upstairs, 218 is my office, and I lead our SPEAR team. We always have a lot of awesome things happening. Student research, internships, scholarships. We do a lot of community outreach in K-12 outreach, supporting our local educators. So if you're kind of excited about those types of things, please check with us and see how you can get involved. If you're a student, these things are look really great on college applications and scholarship applications. So please kind of take note of that. All of our internships, we typically have opportunities to do kind of that outreach part with us. We do have that portable planetarium that stays incredibly busy, and that's kind of a neat thing that you can get involved with as well. I can sit up here and talk about all kinds of things, but I'm just really excited to hear about this presentation tonight. And a bit tired, so I probably don't sound or look that great. So I'm going to go ahead and pass this on to our guests. So Damian, welcome.
I figured it would be given that we give Crystal a round of applause for helping me put this together tonight. Regardless of how many people showed up, we always have fun doing it. And yeah, so you kind of stole my thunder. I had this whole thing planned out. You know, I grew up here, graduated from here, but you guys already heard that. It's always good to come back. So this is kind of designed to around students who are in that SPEAR group, but again, the general community. So thanks everybody for showing up. I know it's a small crowd, but I'd like to say that I know most of you, but I'm actually kind of glad that I don't know every person in this room. There you go.
Awesome. Thank you. Thank you all for having us. So we are Oregon State University's student chapter of the American Institute of Aeronautics and Astronautics. So that's our acronym there, AIAA. We consist of 8 different aerospace-focused projects, and tonight we're going to kind of walk you through what each of our clubs do. And then Ryan over here is a graduate student, and he's going to talk a little bit about the electric propulsion research he does. So I guess we'll start off with introductions. My name is Braden Haldezos, and I am one of the student leaders of our group, and I am also a capstone student or a senior design student on one of our rocketry teams.
Hey everybody, my name is Lucas Knippel. I'm studying electrical and computer engineering at Oregon State, and I am a avionics member on one of our rocket teams.
I'm Damian. I'm the high altitude rocket team lead. I'll talk more about that later, I guess, here in a second, but
I'm Mason. I'm one of our student leaders and also part of the structures team for all solid fuel rocket teams.
I'm Ryan. I'm a first-year mechanical engineering PhD student and former HAIL team lead.
I'm Eric. I'm on the propulsion team member for one of the rocket teams.
I have the clicker.
All right, you can go ahead and click through. Yeah, no worries. Actually, it's back to you.
Oh, perfect. High altitude rocket team. We call ourselves HART. We are the only two-stage rocket team on campus running a dry fuel that we actually mix ourselves. That's a picture of us last year in May in the Mojave Desert. That rocket that's in that picture is the one that's out here, separated into two stages. It flew 64,000 feet in the middle of Mojave Desert in the middle of May last year, yeah. At right around rocket is about 90% designed in-house. The only thing we purchase is actually what you see. All of those tubes are purchased from Innovative Composite Materials or Innovative Composite Engineering, ICE. We just give them dimensions, they send us tubes. We're getting tubes in 3 days for the new rocket. And then everything that we build goes into it. And so this picture up in the top right is what we call a bulkhead. In the past, we do carbon fiber bulkheads, and we've noticed a lot of manufacturing errors in that, just in the consistency in the epoxy mix, because carbon fiber relies on epoxy to be able to join. And when your manufacturing processes are wrong and the epoxy doesn't bond correctly, bulkheads don't look very good. So we actually had these manufactured on a lathe and CNC. So that's going to eliminate that problem. We're also doing a lot of carbon fiber work. So if you have any, how many of you guys are students? Let me just ask you that. Okay, perfect. If any of you guys have any interest in carbon fiber work, this is a really good thing to be a part of. The fin chamfering is just a router table. That's not super exciting, but it's got to be done. And the fillets and finishing is essentially when we put these fins on the body tube, we've got to have a smooth surface that transitions into the fin because you don't want a 90-degree. So we basically 3D printed a jig that would allow us to run a perfect bead of epoxy down the side of these fins to get that perfect transition. But definitely, this is definitely our most hands-on team. A lot of our other teams do a lot of studies analytically on a computer. And if somebody just wants to, spend time in the shop doing carbon fiber layups, structures is where it's at. I have never taken a composites class in my life, but I do a lot of composite work and it's all from these teams. So I think that's all I had. I think, who's next? Design, build, fly. Is that you? Perfect.
All right, our next team is Design, Build, Fly. This team focuses more on an airplane rather than a rocket. You can go to the next slide. The goal of this project is to develop a RC aircraft and go fly it in an international design competition with a bunch of other schools. So we are competing to achieve a certain set of objectives that are set forth by AIAA. They are the host of this. And this year, the challenge involves creating an aircraft that can autonomously fly around a course and complete certain objectives. So you can see an image right there of the plane. They actually just took this image today. They finished grading it. You can go to the next slide. The design features a mothership, which is the plane that you see here. This plane has to go, actually, if you go to the next slide really quick, you can kind of see, yeah, so the plane has to fly in kind of an Olympic track shaped oval. It has to do this 3 times and then complete a series of smaller loops. It's kind of hard to explain, but it has to fly. This mothership has to fly. You can go back to the previous slide. And then underneath it, sitting right under here, there is a mini glider. So it's a plane that deploys a glider. The plane that you see there is manually flown, but the glider has to be autonomously flown. So the glider will detach from the plane and autonomously fly a predetermined route and then land on its own. And you have to land in a very specific area to get points and increase your score. And so I think it's a really awesome concept this year. You can go to the next slide. I think we had a video here, but it won't be playing, but you can come see afterwards. They have a video of the the little glider thing autonomously landing by itself, which I thought was really cool. All the components for this are made in-house. So we use balsa wood and we cut the parts. We design and cut the parts on a laser cutter. And then we integrate electronics into that. And then we program the plane from there. And so there's a lot of manual flying that takes place because we have to train the flight computers to be able to fly the plane autonomously. I don't think they use cameras to see, but they use, I think they use LiDAR or something like that. I'm not on the team, but they use something to be able to like know where the little glider thing is. So I think that's pretty cool, but that's DBF. Next up is the agricultural drone team. This is a really cool project. So this team is also developing something that's autonomous. This drone is being developed in partnership with Raitong Organics Farm. So this is a farm in Thailand, and the whole purpose of this project is to design a farming drone that can go out in the fields just by itself autonomously and farm. I believe it has a payload on it that is capable of carrying liquid, so it can be fertilizer, it can be water, whatever. But you can go to the next slide here. Basically, the drone, yeah, it'll do that again. I don't think the video will play, which sucks, but you can see over there, it has a test flight of the drone flying. This year, the team has mainly been focused on getting the drone flyable because at the beginning of the year, they tried to test fly it and one of the motors wasn't working and it like kind of blew up a little bit. It crashed a little bit. So they've been trying to fix that and do a lot of programming. A big part of this is making the drone repairable using off-the-shelf parts, because if you think about a farmer in a remote part of Thailand, if something on this drone breaks, they're not going to just be able to go manufacture a replacement part. They're going to have to order it online. So you have to design this drone using things that you can find online. That's a very big challenge. Additionally, a big challenge that they haven't had time to focus on this year is how do you make all the components waterproof, because it's very rainy in this area. And additionally, the farmer is probably not going to be very technically inclined. So how do you make it the user interface of the drone very friendly, so anybody can learn how to do it and use it very simply? So these are some of the challenges that the team has been faced with this year. And in my opinion, I think this is one of the coolest teams that we have. But that's me. Next up, we'll pass it on to Hale.
Yeah, I'll take that. Okay, cool. Our video doesn't work. Dang. Okay, so HALE is the high altitude liquid engine team. The other rocket teams that you'll see during this presentation are solid rockets. What that means is the actual motor that they use is a fuel grain that is like a solid mix inside that contains the propellant and oxidizer. They're both propellants, but the fuel and oxidizer in one sort of dried compressed grain. We use liquid propellants. So this is what like Falcon rocket or, you know, the Saturn V or, you know, sort of big orbital class rockets use. So we are a Kerolox system that is kerosene and liquid oxygen. So we're also running cryogenic propellants, things that are, you know, causing all kinds of problems for us, but that's sort of our bag. And so we're a little bit slower than some of these other teams. We're, you know, a sort of long-term iterative, constant march towards getting to our ultimate goal, which is the Kármán line. So that's at about 100,000, or it's about 100 kilometers. It's sort of the beginning of space for aerospace people. And so, that's the wrong, there we go. Cool. And so this is sort of our mission statement. So we design, build, and launch a single-stage liquid bipropellant rocket to the von Kármán line. That's 328,000 feet, 100 kilometers. Pretty fun. Okay. And then
Is this click on the next one?
and then down is next.
All right, so a pretty interesting fact is about when you start working with liquids, all of a sudden your rocket goes away from just being self-contained in its own vehicle that you can light the candle underneath it and use common launch infrastructure, and you have to start developing your own launch infrastructure to handle the cryogenic liquids that you're working with at all times. So our team, not only are we developing our flight vehicle, but in addition to that, we're also developing our own ground control systems so that we can actually enable the launch of this flight vehicle. And so there's sort of two parts to this system. The first thing is when we're developing our engine, we have to isolate the engine, because when we do the propulsion research, that's the most important part about getting the rocket off the ground, is can we actually produce the thrust downwards so that we can go up. And so On the left side here is our horizontal test stand. So this is a bunch of data acquisition, plumbing, and tanks that allow us to put just our engine on the stand and then run controlled tests where we can actually light it and fire it and characterize the engine. When we do a full-scale launch with our flight vehicle on the right side here, this is our vertical test stand. And so this is a massive 30-foot by 10-foot trailer that we take all the components on this horizontal test stand and we put it on there. And then on top of that, we can now facilitate a large launch rail. We're going for about a 50-foot or a 60-foot launch rail, which is just absolutely huge. And we can put our rocket on it and we can run the same thing. And then we light that and we take it off, which is pretty fun. We had some pretty cool videos of our hot fires. This is probably the most exciting part of the team is watching an engine fire. There's no experience quite like it. It's very loud. It's very bright. Our second generation engine, which is our flight capable engine that we'll actually be putting on our rocket. We fired it recently about 3 months ago, our first test, and we fired it at night. And so this is the firing video that we can show you if you guys come outside. And then just recently, gosh, I guess the video doesn't load. So that's another video that we have that's not shown up here, but we have our second static fire of that engine. Next slide. Oh, just the next slide. Oh, I see. Okay. Wonderful. So the main difference between these two firings is the first one was the first time we ever fired the second generation engine. A fun fact is this engine is the second college-developed bipropellant liquid engine rocket ever developed in the state of Oregon, and the first was also ours. Our first generation engine, we brought it along with us today. So if you're at all interested, we have it with us. It's pretty cool. And so this was the second firing. Now that we had a proof of concept that we could actually fire our engine, some changes here we made to some valve timing. We want to characterize the engine a little better, improves thrust with a nozzle that you see right here. And again, if you see the video when you come out, we'll be able to give you a little better detail on that. Alrighty, I'll send that off.
Okay, cool. So, as he sort of set up for me, we designed Mira 1 and Mira 2. Those are our two engines. Mira 1 was, well, you can go out and see it, but it's really big and bulky, weighs like 50 pounds, stainless steel. We mainly were building that so that we could, get something in the stand and get characterizing and building up the infrastructure around running our engines. But it's difficult to integrate an engine like that into a flight vehicle. And so that's what Mira 2 is. Mira 2 is a huge weight cut. It has overall essentially the same performance specifications. There's using some sort of clever tricks to deal with heat and some other things. But that's sort of the idea is we miniaturized Mira 2. Both of our engines are on Wikipedia. That's a big big deal for us rocket nerds. If you look up pintle injected system, which is a pintle injector, like on the things, it's literally like Merlin and like all these real, rockets, and then it's us. And so that's something that we like to show off. So we are a pressure-fed, pintle-injected Kerolox cycle engine. And what that means is there is essentially a really high pressure tank at the top of our rocket that is generating all of the main force to push all of our propellants and feed them into our engine. So it's pressure fed. Pintle injected means we got this little guy. And so what this is it's a little sort of screw-in section with holes drilled in it that are really precisely machined. We EDM these, so electric discharge machining. And it has an annulus, so this little ring around here, that little thin slot, also essentially releases propellant. And so what happens is you have a flow coming out of the annulus that is our aux, and then you have a flow that sprays kind of like a star around it. Oh yeah, here we go. I have the images I forgot here. There we go. So one that sprays like this and one that sprays like that. Those two flows intersect each other and you get this sort of cone shape. And also you get vorticular flows. You get a vortex basically where the fuel and the oxidizer are mixing really, really efficiently. And so all that just is a whole bunch of little like micro infrastructure inside the engine that makes sure that our fuel and our oxidizer are mixed really efficiently. And that gets us the most energy possible out of our propellants. And so this is a little simulation that we did with the nozzle. That's one thing that we've also been working up a lot. We had like internal nozzles and some less efficient nozzles for the first engine series. And so with the second engine series, we just were able to manufacture and test our first nozzle. And so that's really exciting. With our flight profile, we're pretty low. So there's a whole bunch of like weird optimizations that go into making a nozzle for low atmosphere flight, because down here, the atmosphere is really thick. There's a lot of pressure that's compressing the flow coming out of your engine. When you're sort of just like walking around, you don't think that there's a whole bunch of pressure pressing on you, but when you're generating pressure from nowhere, that matters a lot. And so your flow, gets disturbed very heavily, and there's all these kinds of interesting effects that occur. These are Mach diamonds. So when you get supersonic flow, there's all kinds of weird things that occur. But yes, that's propulsion.
All right, so in addition to the propulsion team, they're sort of our main driving force because the whole thing is we're doing liquid rocketry. If we actually want to put an engine and send it up to the sky, we have to have a bunch of other sub-teams building a bunch of other infrastructure. And so we have 5 other sub-teams on the team. And so we're gonna run through these real quick so we don't burn too much time. The first up is our vertical test stand. So I already talked a little bit about that. That is gonna be our 30-foot by 10-foot launch trailer. We're actually gonna drive this thing down I-5 all the way to the Mojave Desert east of LA. And the main purpose of this is to facilitate the fueling and launch and safe launch procedures of our flight vehicle when we actually put on it. The main work that goes into this is a lot of machining and manufacturing and fluids work. So we have to understand how we get a fluid from point A to point B, how we do that safely. And then when I talk about avionics in just a sec, how do we know if we're doing it safely using data acquisition systems, sensors, and such. As well as the final launch that we'll actually do in the Mojave Desert. Before we go all the way out there and we cross our fingers and we send it up, we're gonna do a lot of tests. We're engineers, so we have to make sure it works before we actually get there. And so that's where the vertical test stand comes in. That's why we don't just call it a mobile launch trailer. This facilitates a lot of tests, both pressure, fluids, electronics, and of the engine before we ever get down there to a launch. So we can validate that system.
So another thing that comes with having those liquid energetic fluids is we need to have basically a whole fluids team in the actual vehicle to deliver all these things to where they need to go. So in between that pressurant tank and the engine, there is a liquid oxygen and a fuel tank. All of those tanks need to have essentially valves and releases and escapes so that anytime there might be a failure in the system, we can either vent it to a safe area or prevent like a catastrophic destruction of the whole system, because there are areas that can see very, very high pressures and areas that need to see much lower pressures. And then add on top of that, all of these systems being actuated are all pneumatics. So we're also driving all of the opening and closing of the valves with that same pressure that we're using to press all of the fluids through the system. So you sort of get into a chicken and an egg where you need like the pressure in order to get all the valves open in order to get the rocket going, which you need for all of your valves and your systems to be running and all your data to be collecting, but that's what we do. And so that's sort of what fluids is getting all those inner workings and cryogenic handling issues through a bunch of valves and tap offs and things. So there we go. And structures very similar to the other rocket teams with a few key differences. You can see our bulkheads are a little bit bigger, a little bit beefier. We're carrying these big heavy tanks, and we have a big heavy rocket, and we make up for that with a very strong, powerful engine. But so these are like a bunch of like intersections. There's a bunch of things for a V-bay, and our design has carbon fiber sort of like flight skin, but the actual structure is mostly aluminum. And so we're sort of building it a little bit robustly and heavy the first time and just trying to get something off the ground. Liquid's very difficult. There haven't even been that many launches in like the whole US period in liquids. And so that's sort of a little bit safer of a design philosophy there. But still, we have a lot of interesting things going on. We have to worry a lot more about accessibility. So when the actual rocket is stacked, being able to mess around with all of those valves and fittings and everything and make sure everything is sealed up is like a very key importance, because if you have one leak in the system, that can be really bad. And when you have hundreds of connections in the system, you're going to have some leaks. So we have like these big channels and areas cut out of the structure so that we can potentially, get in there and eventually have to, fix and mess with things. Because it's not always just gonna, everything turns on, it all seals the first time. So, a few other little things like that, but some other considerations. And then aero and recovery is an interesting one. So our rocket is huge. It weighs like what now? Like 300 pounds. So how heavy is like the heart rocket or?
Short.
Yeah, short of 80. So pretty big. We need to have some big parachutes. We need to do a dual deploy. Essentially, if you deployed our big, huge parachute up at the altitude where we would want to deploy it, we would drift like really, really far. And so we need to have a little teeny tiny parachute that starts first so that we're falling much quicker, and then the larger parachute deploys. So dual deploy, we have to have a sort of another place where we're reusing the high pressure and gas. They use like a pyrotechnic charge to separate and kick things off. We actually have that high pressure gas tap off into a little piston, and the piston punches off the nose cone. So, some other sort of considerations around that, and the fin's mostly the same fin can kind of layup thing. We've combined a lot of that. And then avionics.
All right, and so this is the final sub team. This is the work I do. So if anyone's interested in electronics, I love talking about this stuff. I'll make this quick because we're running a little long. So avionics is all about doing the data acquisition and control of the rocket. We cannot stand next to this and turn all the knobs and look at all the gauges and feel good about our safety because we're next to very high pressure fluids and very dangerous and explosive fluids. So when we have to launch a rocket, at minimum, we're gonna be 400 feet away in a subterranean bunker, just barely looking through some very thick plexiglass with some ballistic covers over on top of us. So avionics is all about tapping the pressure, the temperature off the system, as well as actuating solenoids and doing real world error checking with limit switches to know whether or not that solenoid turned to open or close a valve. And so what I mean by that is there's a lever arm on that valve that's gonna move physically, and we have a little button right here and there to know if it actually made it there in the real world. So we've had problems with that, and that's very important to make a safe system. Everything or most of everything we do is in-house design. So we're a bunch of electrical and computer science and mechanical engineers, and we love this stuff. And so we try to design systems where we can, but we're also not trying to reinvent the wheel. So where we can take off-the-shelf solutions, we go for that. All of this work combined, we are hoping to launch our subscale vehicle this summer. It is a 20-foot rocket, which is crazy because it's our subscale rocket, and we're aiming for a 30,000 feet altitude. That's Hale. I'm going to pass it off back to Braden for APOP.
Just down button. Down button.
All right, so APOP is our Aerospace Propulsion Outreach Program team. This is a design competition, national, sponsored by the Air Force, in which the team is given a JetCat engine, you can see in the bottom right there, and they have to do something to it. So this year, the team is focused on creating a nozzle, which you can see a very preliminary draft of right here, that is capable of throttling to adjust the amount of thrust that the engine produces. So you can see sort of iterations here. Over on the right is their initial design concept when it's closed. So that's when you would be generating the least amount of thrust. When you go over to the middle and the little flaps right here open up, you can throttle the thrust to produce more, and then you can actually see the fully prototype model right here. So we go and we compete with a bunch of other schools at, I forget the name of the Air Force Base in Ohio, but that's where it is. And I forget the exact metrics, but I think you have to design this so that it can precisely throttle to about 80% of what the normal nominal thrust would be from the engine. So that's sort of the objectives there. You can, we had a video to play, but you can see sort of what it looks like on the engine up there in the top right. Again, that's an early design though. And if you want to see the video of that thing working in action, you can come see it after. Next up is our solar airplane team. This is a research team that is aiming to, oh wait, you want to talk about this?
I can take it.
Yeah, you talk about this.
Okay.
Yeah. He's actually on the team, so.
Yeah, yeah. So Solar Plane is our other plane team. We got two. DBF is the first, Solar Plane's the second. Whereas DBF is a competition team, Solar Plane is a research team. And what they're researching is the idea of pseudo satellites. So right now, if we want to put something up in the air and we want to keep it up there, we have to put it in low Earth orbit. And that takes a lot of energy, that takes rocket science, and that's very complicated and very hard, to be quite frank. And so the solar plane concept is, what if we could launch a plane and it's light enough and efficient enough and it has solar panels on it that we could send it up and it'll be able to power and recharge itself theoretically infinitely. And so now you don't have to use all this energy to put something in orbit, but you still have the same characteristics of something up in the air that you could use for anything like broadband or any like GPS, the same functions we use for satellites today. The main objectives of this one is you're gonna have almost no launch costs when you do this, no emissions, you can provide communication, surveillance, internet, etc. The team this year is taking an off-the-shelf RC glider, and they're upgrading it with all these solar panels and solar plane technology like electric motors in order to meet this goal. So last year's team, they got a 2-hour flight time in with a single boom or a single fuselage. What I mean by that is, if we look here, this is just one fuselage of the plane. So this year, the team, they were experiencing a lot of wing bending problems where when they're producing all the lift across the wing, it starts creating this kind of V force on the wings, and it creates kind of like a snapping moment right in the middle. And that's not very good as far as if you want to create a safe plane to put up. And so they're making 2 booms this time to sort of distribute that weight load and make it a lot safer. On top of that, they are aiming to carry significant payload, so about 10% of the airplane's mass, between these 2 booms. And so they actually just had their first flight, not their first flight, they had a pretty cool flight. The first flight, they put a camera on as their payload. And again, we have that video and we can show it to you if you come out and meet us in the lobby. That would have been that video. It's pretty cool. We have a drone chasing it in this case. By the way, the scale of this thing, I think they're rocking 12 feet. Does anybody remember?
12-ish.
Yeah, it's absolutely huge. So if we put it on this stage, it's gonna be very nearly reaching across this stage. And the purpose behind that is, as you extend the length of an airplane's wing for sort of the same width that you have a higher wing to aspect ratio, which gives you more efficient characteristics from the plane. So that's what that's all about. It's pretty cool. And pass it off back to Brayden.
All right, and lastly is our student competition rocketry team. So this is our 3rd rocketry team here. We are again a solid team, and we are unique because unlike all the teams you've been hearing from where they are a majority led by senior design capstone students, this team is primarily led by underclassmen volunteers. We are also a competition team, so we actually go compete in an international design challenge with other schools down in New Mexico. And additionally, we have a payload in this rocket. So we're going to talk about the payload soon. We've already, this rocket has some of the basic subsystems, structures, avionics recovery that you've been hearing from the other teams. So we're not going to cover that, but we are going to cover both the payload of this rocket and an additional aspect that makes it pretty unique. So I'll pass it off to Mason to talk about Beavs.
Yeah, so Beavs, or blade extending apogee variant system, you can see up on the top right there, is our airblade system, because as a part of this competition, you're trying to reach an exact altitude. So for us this year, that's 10,000 feet. And you score more points if the closer you are. So the point of the airblades is, as we're going up, it uses a PID loop to detect what its expected apogee is based on velocity, altitude, and some other data it collects. And then extend the blades to decrease our altitude so we get to that exact goal.
Yeah, the video's up there playing. It's really cool in action, so you can come check it out afterwards. The payload, on the other hand, so this is the Planetary Exploration Mapping and Data Analysis System, or PEMDAS. The goal of this is pretty cool. So this is a CubeSat payload that replicates what you would send to a potentially habitable planet to determine its potential for human life. So the idea here is that, you send our rocket to a planet and then you deploy this payload. And on the way down, while the rocket is descending, the payload collects a lot of atmospheric data and just data about your environment. There's a camera on it that takes pictures of what the ground looks like and then uses photo meshing to determine optimal landing sites for future human crewed missions. Once the payload actually lands, there is a soil sampler, which you can see right here. And it's got this little double door thing that'll kind of open up and, like Hungry Hippo style, it'll like scoop dirt in. And then it will analyze that dirt. It will mix it with a water sample, and we can determine the material composition of the soil. And so there's a lot of really cool things that this payload can do. And that's what makes our team unique. Now, that's it for all the AIAA teams. That's all of our teams. I'll pass it on to Ryan now to talk a little bit about what he does.
Okay, cool. So I also wanted to represent the graduate program at Oregon State University. And so this is sort of going over sort of the vision that at least my lab with Professor Richard Wurz has for aerospace in Oregon. So we are an aerospace and energy lab. So we do stuff in advanced aerospace propulsion and also in advanced energy concepts. So sort of the like focal point of that is it's always having to do with plasmas and plasma physics. So for advanced propulsion concepts, whether it's EP, electric propulsion, which is using like the electrostatic force essentially to charge up some particles and get much, much higher velocities than what a chemical propulsion system like HALE uses can get. Or fusion propulsion, or trying to do something like a fusion. Oh, it's not on there. Oh, it's. Do I have it? Yeah, there we go. It'll be on the next one. Okay. Or fusion. That's sort of the sort of environment that we inhabit, and so we have this sort of umbrella within OSU. So we do stuff with College of Science and Engineering and some others, and so we basically are developing advanced materials to sort of exist in these plasma-rich environments. And we're funded through some government programs, and that's that. There we go. Cool. So these are sort of the environments that we deal in. When I say extreme environments, I really mean it. Particles that are hitting our materials are going 20 kilometers per second. So like they can do the whole drive that we did from here to Corvallis in like, I don't know, 3 seconds or something. It's about 20 times the speed of a high power rifle round. We frequently make materials that survive temperatures at the surface of the sun. We're working on doing temperatures at the core of the sun. We are pretty crazy with what we build materials for. So all of that is sort of seated within these sort of programs and sort of capabilities that we have at OSU. So we have advanced manufacturing techniques, and we make graded and tailored alloys, which is essentially making alloys out of some all kinds of different exotic metals, ceramics, and using additive manufacturing techniques like laser powder bed fusion, direct energy deposition, binder jet, and some other things. We're close to the HP campus and Atami, and so we utilize those resources. And so we're also developing tools and data sets and all kinds of things, AI, a lot of analysis for essentially creating these sort of new and exotic materials. And so that whole thing is AMIA, Advanced Materials and Manufacturing for Energy and Aerospace. And so we partner with businesses like HP and sort of large aerospace providers, as well as academia and national laboratories, and sort of knit all of those things together from their interests and their experience to their resources in order to make some of the craziest materials in the world, definitely in Oregon. And Oregon actually is a really good place for opportunities for advanced materials. All of the arrows that we have exploding out of this are labs and things that have used our materials. There are immense federal needs for these advanced materials, and Oregon has some of the only like built up infrastructure to develop some of these things. So it's really an advantage that particularly Oregon is seated to make use of. We had a lot of sort of like older companies that were already sort of in this area. So, we have a lot of connections with people who made like titaniums and castings and things. And so we have a lot of sort of spin out companies that have been developing that stuff that are already here. And that stuff is not easy to just whip up out of nowhere. So for now and for the foreseeable future, we're going to have a pretty good advantage in materials that we're looking to exploit. And so sort of showing that OSU is doubling down on this, we are building a new laboratory. So it's the Collaborative Aerospace Research Center at OSU within the Nancy Squires Aerospace Laboratory, which is actually where Hale and some of the other teams conduct their experiments. This is sort of just a little floor plan thing we have developed, and we have a couple nice photos showing what it might look like. These are all vacuum chambers. We have to mimic the space environment when we are testing our advanced propulsion things. And so you'd be like, oh, how could you fire a rocket engine inside of one of these things? Pretty much that's kind of what we're going with. Luckily, we don't have to deal with as much thrust. The the advanced propulsion stuff that we make usually has thrust about a sheet of paper, but it's like 10 times more fuel efficient than those engines. So as long as you're already in orbit, if you're a spacecraft and can burn for a long time, it works out that it's much more efficient. And so we can actually test those propulsion systems inside of these chambers. So here's another little image of that. Cool. And so we are continuously trying to develop an organ space identity and sort of the capabilities around that identity. So we're using those material strengths that already exist here. We're growing the community at all different levels, including within AIAA, which is why it's important to come and do these kinds of outreach events and get more people interested and show everything. And so we're just trying to, keep improving research, keep investing in this areas, and, just sort of engaging everyone and getting everybody ready so that, from K-12 all the way to me, grad student working on a PhD, we have people who are ready to, do these things. So there we go. That's graduate studies within the WERS lab.
All right, so that about does it. Thank you all for coming. To the students in the crowd, we didn't really get to touch on it, but we've all had experiences with internships and other career development programs that we would love to talk to you all about. So come and talk to us. But other than that, thank you all for your time.
Thank you. Thank you all. That was an awesome display of everything you guys do. And I know there's so much more, and I'm sorry about the videos. But yes, if any of you would like to come see those videos, I encourage you to please come out here and also check out the things that they set up on the tables. So again, thank you to everybody who came out tonight. And for those of you that may or may not be online, because we had technical issues earlier, but we will be posting the videos online. If for some reason it went off live, you'll be able to watch us a bit later. So yes.
Yeah, so we actually work with NASA to get funded. We apply for, we write proposals every year to get funding from NASA, various other companies. We receive funding from our school as well, so we get support from them and the faculty that are in the school. We actually just started working with Boeing and Blue Origin too. They mentor us during our design reviews for several of our rocket teams, and we actually like to pay it forward too, and we mentor high school students and we do the design reviews for them. So yes, we work with a lot of people. I also love NASA, so yeah. Yes, yes.
It was something we also forgot to mention that we usually do at the beginning. I had everybody who was a student raise their hand at the beginning of this. There's always been a big misconception with teams that are as big as this. I understand that we have Spear here doing smaller scale research projects, but I get questions a lot about what does it take to be a part of these teams, and the answer is nothing. I mean, for you people who are sophomores, you can transfer Oregon State and see you in the fall. Like, let's get to work. Let's do it.
Pretty much all of us start out with no experience, so.
Well, thank you. Yeah, earlier I typically mention, but Oregon NASA Space Grant, they've been huge supporters for, like, I know our Spear team, and we're doing that K-12 outreach. We're trying to keep inspiring that next generation. So that's always important. Our community here, this college administration, everybody's been a huge, huge support for all that we do. So it's awesome to see kind of that next step, and we're kind of continuing on. We have the Oregon Coast STEM Hub also. We'd always like to kind of give a shout out to, we're doing high school STEM internships now, where we can actually get some of the students 16 to 18, get them in here, get it going, and then maybe pass them on to you all. So we are going to be over there at Oregon State with some of our team on the new symposium date that had to be moved because of the weather, April 11th. So if any of you guys are around, if we could possibly maybe come say hi, that would be great. And maybe even set up maybe a future, a remote type of meeting with other students that weren't able to be here today. So, all right. Well, with that said, if everybody wants to give them another round of applause and then come out here and check out their stuff. Thank you. Doing that. So yeah, I'll be there the whole time, and then some of us, Dr. our geology professor, she's up to faculty to faculty research board that we were so pretty good sized team that's going to be coming up along with the 3 other faculty members. So it'll be cool. Well, yeah, we love
Doing good.
I'm gonna get
She was super stoked when you called her and said this, like,
Yeah.
guess what?
It's pretty cool stuff. It's fun to talk about because, you know, a lot of people, they're asking me what we're doing.